Hi, in this tutorial, I'm going to show you how to create a Pearl Bubble Tea Shattering effect with Phoenix and tyFlow and render it out with V-Ray GPU. Those are the topics I'm going to cover in this video. And I use specific software to create this scene. Now, let's begin. First, let's talk about modeling. Our main model is this glass cup, and we've modeled it to be 25 centimeters tall at real size with some thickness. It is a solid, watertight model with no errors when the STL check modifier is applied. To save time when filling this cup with liquid, we have prepared a geometry for the liquid source. Let's refer to this model as box initial fill. So how can we quickly and precisely create this special geometry? Actually, the procedure has been explained in the article titled Using Initial Liquid Fill with Containers tutorial on the official Phoenix help page. You can refer to this article for more information. Let me quickly demonstrate how to create it. Start with the glass cup in the scene. Create a box with segments set to 1 for all sides. Adjust the size of the box. The top face represents the height of the liquid in the cup. The remaining part of the box should cover the glass cup like so. Next, with the box selected, go to the Create panel, Geometry, Compound Objects, Pro Boolean. In the Pick Boolean rollout, set the type to copy. In the Parameters rollout, set the operation to subtraction. Then click the Start Picking button and select the glass cup's geometry. This will subtract the glass cup from the box while keeping the box geometry. In the Modify panel, right-click the Pro Boolean modifier and convert it to an editable poly. Switch the selection to Element. Select the part of the box outside the glass and delete them. Remove all other unwanted meshes. And voila, the mesh for liquid emission is ready for us. In addition to the cup and the liquid, we have also created 2 helper geometries, 2 spheres around the cup. We will use these to control the distribution of the point cloud for Voronoi fracture. We will discuss how to use them later. Now that we have shown you the scene geometries and the helper objects, we can proceed to the particle system, that is tyFlow. Open the tyFlow editor. We have 3 major events here, one for the glass cup shattering, one for the bullet, and one for the pearl bubbles. Let's start with the simplest event, the shooting of a bullet. To start, the birth operator said to create a single particle at frame 18. And we have placed a tie icon helper in the scene which points to the glass cup. We added the tie icon in the position icon operator and gave the particle a speed of 3 centimeters and a geosphere shape. We added a physics shape to the event so that tyFlow will calculate the rigid body simulation for it. The hull mode is set to mesh for better collision accuracy. We set the physics switch to kinematic to allow the bullet to push the rigid body of the glass cup and its fragments. The action is only one way, so the metal ball won't be pushed back by the glass fragments. Now let's talk about another important thing, the glass cup breaking into pieces. We use the birth object to import the glass cup geometry. The property test operator is employed to detect the incoming bullet or metal ball, with the test type set to neighbor count and a search radius of 5 centimeters. When the test is true, it triggers the next operator, the Voronoi fracture. As you can see in the preview, when the bullet approaches, the glass cup begins to crack. The Voronoi fracture is the operator we use to break the cup. Basically, the more points parameter is set, the more fragments you get. However, you get only homogeneous fragments. That's why we use 2 spheres to create higher density areas locally. As you can see, we get smaller fragments around the 2 spheres where the bullet hits. By default, the glass cup would break into pieces immediately upon the bullet impact. That's why we introduced the physics bind glue operator in the event. It glues some of the fragments together, providing the option to break those bonds. This adds extra realism to the simulation. As you know, tyFlow comes with default fixed settings for gravity and a ground collider, which can be useful for beginners. However, we turn these options off for greater flexibility. For example, if we want different events with varying strengths of gravity, or if we want to use custom geometry for the ground, so we added the physics collision and force operators in the tyFlow event. Add our custom floor geometry to the colliders list of the physics collider and set the gravity to minus 0.04 centimeters. Now, let's focus on the event for bubbles. Filling a geometry with spheres is not difficult, but the tricky part is making sure they don't penetrate each other. This can be achieved with the help of VDB-related operators. First, create a grid container using birth VDB. Here, we set the voxel size to 1.0 centimeters as the size for the pearls. We use the same geometry to fill up the cup for liquid source, but with some modifications since the cup is not entirely filled with pearls. We apply a slice modifier to the geometry to control how many pearls fill the cup, simply by moving up and down the slice plane. On top of that, we added a push modifier to it to create more space between the glass cup and pearls, preventing any possible penetration between them. Select the box fill pearl in the objects list of Object to SDF. Next, convert the VDB to particles, setting both the min and max radius to 1.0 centimeters as all the pearls are of the same size, and assign it a sphere shape. To let the pearls fall, we add a force operator here, with the strength set to minus 0.04 centimeters. But for the timing of the force, we switch to frame because we don't want the pearls to fall when they are inside the liquid, so we set the time range from frame 29 to 1000. Frame 29 is when the metal ball hits the glass cup. Let's see the particle preview again. We are viewing it from a different perspective so you can see better. To make the shot more impactful, we added a wind force in the scene. The wind is pointed towards the camera so that pearls can fly toward it. As you can see, many pearls are now flying toward the camera, making the shot more interesting. All right, we've explained all the important operators for the glass cup, the bullet, and the pearl bubbles. There's still something more. For all the events, we added a particle groups operator to them. This allows them to communicate with each other in terms of rigid body simulation. For example, in the pearls event, we set the simulation groups to 1, as in other events. This way, all the particles in the same simulation group will collide with each other. Talking about particle simulation in the simulation section of the tyFlow settings, we increase the substeps to 40 for higher accuracy for the rigid body collision. Besides the particle groups operator, we also added material ID operator to every event. For the glass cup shattering, we set the ID to 1. For the bullet, we set the ID to 2. And for the pearl bubbles, we set the ID to 3. By doing so, when we later export the particles as meshes, we can assign them a multi-sub-object material, with each part having the correct material applied. We have explained every operator for the particle effect. Now let's talk about the slow motion effect or bullet time. Here is the preview with normal speed. tyFlow comes with a very intuitive retiming option. We can use retimer by speed and keyframe the speed percent to achieve the desired effect. When the speed percent is set to 100%, it means the particles are running at normal speed. When the speed percent is set to 10%, it indicates they are slowed down to 10%. So, in the beginning, we set the speed percent to 100 until frame 29, it gradually drops to 5% by frame 37, and remains at 5% until frame 55. Then, at frame 61, the speed picks back up to 70%. By animating this parameter, we can achieve the bullet effect we're after. Alright, our particles are all set. Now let's export them using the Export Particles operator. Set the export mode to Objects. Click on the Generate Objects from Particles button. After export, you will get around 600 tyFlow node objects in the scene. Disable the tyFlow because we don't need it anymore. With the completion of the rigid body simulation, destruction, and bullet time effects, we now have the necessary elements to integrate them into a fluid simulation using Phoenix. Let's start by creating a liquid source and adding the box initial fill geometry we just created in the emitter nodes. Instead of using surface force mode, switch to volume brush. This will brush out the volume with liquid. Note that we didn't use the initial fill option in the Phoenix properties of the box initial fill, because, though it fills the cup initially for one frame, the simulated liquid will lose some of its volume very quickly. This happens due to the low scene scale and can be overcome with more steps per frame or increasing the scene scale, but in our case, this will either make the sim slower or change the liquid behavior. We aim to achieve a perfectly stationary filled liquid in the cup. That's why we choose to brush out the liquid for several frames to bypass this issue. Let's animate the brush effect percent parameter to sustain at 100% until frame 34. This means Phoenix will brush out liquid from the box initial fill geometry until frame 34. Note that the glass cup explodes at frame 30. Next, we create a liquid simulator aligned with the camera. The initial grid covers the region of the glass cup, and we enable the adaptive grid so the simulation grid expands when the glass explodes. This option allows us to have a smaller grid size initially, and then expand the grid when necessary, saving us some simulation time. Once the grid and source are set, we are ready for the fluid simulation. But before that, since there are many objects in the scene, to avoid any unwanted interactions in the scene interaction rollout of the simulator, let's switch to the include list and add the liquid source, box initial fill, the floor, the background wall, and all the exported tyFlow meshes to the list. The fluid in this example is actually very simple and doesn't need much adjustment. The key is to fine-tune the gravity and steps per frame. Setting a low value for gravity prevents the liquid from falling too quickly, while a high steps per frame value ensures a smoother liquid mesh with minimal holes. Okay, we are all set for fluid dynamics basically. We still need to do more for the bullet time effect. Since we have already set up bullet time with tyFlow for the particle simulation, here in Phoenix, we simply do the same thing. Animate the timescale parameter and set keyframes for it. The curve is basically aligned with tyFlow's retimer speed percent. So in the beginning, we set the timescale to 1. Until frame 29, it gradually drops to 0.1 by frame 37 and remains at 0.1 until frame 55. Then, at frame 61, the timescale goes back up to 0.7. Surface tension controls the force produced by the curvature of the liquid surface. But what exactly does surface tension do? The surface tension algorithm essentially takes the positions of the liquid particles and corrects them. Here, we give it a value of 0.05. A value of 0.05 is strong enough for the effect we are after. If it's too strong, it will look more like jelly or glue than liquid tea. Droplet formation is set low because we want to have a more sheet-like liquid mesh than forming droplets too quickly. However, the effect of surface tension becomes more pronounced at a low timescale. This is because if the timescale is higher, the liquid would be able to travel more distance between each correction. If the timescale is lower, the liquid would be able to travel less between each correction, and this is why the corrections would give a better result, making the surface tension appear stronger. Therefore, it is necessary to animate the surface tension according to the animated timescale to compensate for the effect. So in the first frame, we set the surface tension to 0.05 and keep the same value until frame 29. Then the value drops to 0.02 at frame 37, sustaining that value for 18 frames. Afterward, the surface tension goes back up to 0.04 at frame 61. Okay, we are ready to run the simulation, and we don't need to simulate the full animation. Set the start frame at frame 27. After the simulation is completed, to maintain the liquid's fill and keep it stationary before the bullet hits, navigate to the input rollout of the simulator. Switch the mode to cache index and animate its value. Starting from frame 0, set the cache index to 27 and maintain this value until frame 27. Then at frame 120, set it to 120. This way, we can achieve a glass cup filled with liquid that remains perfectly still until the ball hits. Previously, we set the brushing out in the liquid source, which is sufficient to keep the liquid still for a few frames. However, since the simulation starts at frame 27, there will be no data before frame 27. Using linear mode for the input won't work for this reason. That's why we're switching to cache index and animating its value. And this is the result of our fluid simulation, which combines rigid body and destruction in the bullet time effect. Finally, we have reached the last stage of the process, shading and rendering with V-Ray GPU. The lighting for this scene is quite simple. We use a V-Ray dome light with an HDRI map. And remember, we added a material ID operator to each event in the tyFlow particles, with the glass cup set to ID 1, the metal ball to ID 2, and the pearl bubbles to ID 3. So we apply a multi-submaterial to all the exported meshes from tyFlow. In slot 1, we set a glass material for the cup, in slot 2, a chrome ball material, and in slot 3, a translucent material using the V-Ray material for pearls. The material for the glass cup is very basic, using the V-Ray material with reflection and refraction colors set to white. Set the reflection glossiness to 0.95. We set the max depth to 32 for reflection and refraction due to numerous glass fragments in the scene. This allows rays to be traced more times. enhancing the realism and visual appeal of reflections and refractions in the rendering. The material for the metal ball is even simpler. Just use the V-Ray material and apply the chrome preset, and that's it. The material for pearls required more tweaking. To speed up your iteration process, first, navigate to the Preference tab of V-Ray GPU and temporarily enable Override Depth, setting it to 8. Additionally, disable Depth of Field and Motion Blur in the V-Ray camera to ensure a swifter iteration experience. Now, let's press the Start IPR button for interactive rendering. Watch as the renderer progressively cleans up the image. Enable the region render for a faster update in the VFB. Open the material editor. Since the pearls are translucent, set the diffuse color to black. Adjust the reflection and refraction to a light gray color. Switch the translucency option to SSS and give the scatter radius a brown color. Tweak the scale parameter until you achieve the desired look of the pearls in the VFB. Reduce the reflection glossiness to 0.8 for a more realistic reflection in the pearls. And those are our final settings for the pearl material. In creating the milk tea material, you also need to adjust several parameters. Again, I recommend using IPR while setting up this material. Since it's a translucent material with some reflection and refraction, there might be some trial and error until you get the exact color and look you want. You can extract colors from a real photo of milk tea and use that as a starting point to tweak parameters until you achieve the desired look. In the end, I gave the reflection a light gray color with a reflection glossiness set to 0.9. The refraction is set to a white color. The translucency is set to volumetric with a brown color for the fog, and the depth is set to 1 centimeter. Apply this material to the liquid simulator, and we achieve a pretty decent look for milk tea shading. You might have noticed that we enabled depth of field in the camera, resulting in a beautiful optical effect in the rendering. In addition to the proper combination of focal length, f-number, and shutter speed, we enabled bokeh effects and set the blades to 7, rotation to 15 with center bias to 1. That's why you see the heptagon in the droplet out of focus and the subtle but realistic look in the shading. Recreating real camera settings with the V-Ray camera makes the final rendering even more realistic. With the materials applied, we can start setting up for the renderer. Here we choose V-Ray GPU because it takes less time to get results. Set the sampler to bucket and the noise limit to 0.005. To avoid flickering, we also set the light cache to animation. However, when you render the initial few frames of the animation, you will notice some artifacts in the area where the liquid contacts the glass wall. This is not due to a shading problem. It actually happened in the liquid mesh. Because the simulation is based on a grid, you get jagged faces on the side of the liquid. Smoothing helps reduce artifacts, but when you set the smoothness too high, you also lose details in the mesh. The solution here is to decrease the ISO surface level of the rendering to 0.2, making the liquid body appear thicker. Then use the geometry of the glass cup to trim off the edges of the liquid, using cutter geometry in combination with invert cutter. Note tyFlow node 691, which represents the mesh when the glass cup is still intact. Now, we have a very smooth liquid mesh. Since tyFlow node 691 only stays active until frame 30, you can keep the cutter geometry and invert cutter enabled throughout the entire animation. There is no need to switch them off. However, you need to animate the ISO surface level value. Make sure to maintain it at 0.2 until frame 30 and increase it to 0.5 at frame 31. In this tutorial, I demonstrated creating a milk tea shattering effect with tyFlow and Phoenix, using a solid glass model and 2 spheres for improved glass cup fracturing. tyFlow handled the rigid body simulation and destruction. VDB filled the cup with pearls, and a wind force made them fly towards the camera. The intuitive retimer option in tyFlow achieved the bullet time effect. In Phoenix, we optimize liquid flow by setting low gravity and SPF to 6, resulting in a smoother sheet of water. Bullet time is achieved through timescale animation, coupled with surface tension adjustments. For a steady liquid fill, we utilize the cache mode in the simulator's input and animate the value of the direct cache index. We use V-Ray GPU for the final render, and tyFlow particles received a multi-sub material for the glass cup, metal ball, and pearls. IPR streamlined material tweaking, and the bokeh effect enhanced realism. Lastly, cutter geometry with isosurface level fixed liquid mesh artifacts. Make sure to take a look at the rest of the Phoenix videos on our YouTube channel. I hope you found this tutorial useful. See you soon.